everyone. I'm going to start with chapter 2 this morning and look at all the stuff we did with derivatives. First of all, we did the definition of derivative, and there were two types that we looked at there. So one was our general definition of derivative, which was f prime of x equals the limit as delta x approaches 0, f of x plus delta x minus f of x all over delta x. And then we also had our definition of derivative at a specific point, which was f prime of x equals the limit as x approaches c of f of x minus f of c all over x minus c. So those were our two definitions of derivative. We talked about differentiability. If it was at a specific point, we had to make sure the function was continuous at that point, and the derivative was also continuous at that point as well. Our different differentiation techniques we looked at, we had our standard power, product, and quotient rule, but we also talked about implicit. We had chain rule. We had parametric. And we had polar. And then we had our different types of application questions also in chapter 2. So first, let's talk about differentiability. So a function has to be continuous before it can be even considered to be differentiable. So first, we have to make sure that our two pieces here actually connect at x equals 2, which means you want to show me that the limit as x approaches 2 from the right of f of x is equal to the limit as x approaches 2 from the left of f of x. So if I use 2 from the right, I have to use the lower equation, which would be the limit as x approaches 2 from the right of 4ax plus bx cubed. And the limit as x approaches 2 from the left of f of x, I'll use the top function, ax squared minus bx plus 3. So substituting x equals 2, you get 8a plus 8b. And recall, as soon as I substitute in the number, I don't need to write limit anymore. If I substitute in x equals 2 on the right-hand side, you get 4a minus 2b plus 3. So there's your first equation. But this one we actually want to do differentiability. So I also have to make sure that the derivatives are continuous, which means I want my limit as x approaches 2 from the right of f prime of x to equal my limit as x approaches 2 from the left of f prime of x. So if x approaches 2 from the right, we're going to use, again, the lower function. So that derivative is 4a plus 3b x squared. And the limit as x approaches 2 from the left, we're going to use the top function, which derivative is 2ax minus b. So again, substituting x equals 2, I end up with the equation 4a plus 12b. On the right-hand side, I get 4a minus b. So these are the two equations that I would use to solve to make sure the function is differentiable. Notice the a's cancel out, so our final answer will be b equals 0. And if b equals 0, then I believe that a ends up equaling 3/4. All right, so different differentiation techniques. Now, I'm not going to go through power rule or product or quotient rule because you should be pretty comfortable with those right now. I do want to practice the chain rule with something which also involves simplifying. So this one, we will do a quotient rule. So our bottom function times the derivative of the numerator, 5x squared minus 7 squared, and then derivative of the inside for our chain rule, minus our top function, 5x squared minus 7 cubed, times the derivative of our bottom, 2x cubed plus 3 to the first power, times the derivative of the inside, which is 6x squared, all over the denominator squared. Right, so just to kind of review, simplifying doesn't mean we're going to multiply it out. Instead, I want to factor. So if you notice in both terms, it looks like I can factor out a 2x cubed plus 3 to the first power. I can factor out a 5x squared minus 7 squared. I've got a 30x and a 12x squared, so I will also factor out a 6x. And then whatever's left over, I will eventually combine together. So if I factor out a 2x cubed plus 3, then I have a 2x cubed plus 3 left in the first term. 5x squared minus 7 is completely factor out. And 30x divided by 6x, there's a 5 left over. In the second one, I have a 5x squared minus 7. Let's see, the 2x cubed plus 3 completely factors out. The 12x squared divided by 6x, you're going to end up with a 2x left over from that term. And in the denominator, 2x cubed plus 3 to the 4th. So now notice one of the 2x cubes factor out. So my final answer is going to be 5x squared minus 7 squared, 6x, and then if I multiply this out, I'll have 10x cubed plus 15 minus 10x cubed plus 14x. So it looks like the 10x cubes will cancel out eventually. And 2x cubed plus 3 cubed. So the final answer in simplified form would be 5x squared minus 7 squared, 6x, 15 plus 14x, all over 2x cubed plus 3 cubed. We did implicit differentiation, so that's when you couldn't solve for y, and you basically had to take the derivative of both sides with respect to x. But anytime you took the derivative of a y expression, technically you were using chain rule, because y itself was a function of x. So you kind of had a function inside the function. So on the left side here, you would have 5x, and then negative sine y, dy dx, plus cosine y times 5. On the right-hand side, 8x plus 3y squared dy dx. And then you had to solve for dy dx, so you move terms around and then factor to solve for dy dx. So dy dx is going to equal 8x minus 5 cosine y all over negative 5x sine y minus 3y squared. So subtracted the 5 cosine y to the right, subtracted 3y squared to the left, and did some factoring, and then solved it out. So that is dy dx. Now we also did second derivative, which means I want to take the derivative of dy dx. But again, everywhere there is a y, I need to make sure I use dy dx in my derivative. So my second derivative, dy squared y over dx squared, is my bottom function, negative 5x sine y minus 3y squared times the derivative of the top, 8 plus 5 sine y dy dx minus the top function, so I'll put that down here, 8x minus 5 cosine y times the derivative of the bottom. And the bottom, notice I'm going to have to use product rule, so that's negative 5x cosine y dy dx minus 5 sine y minus 6y dy dx. So that entire thing is divided by your denominator, negative 5x sine y minus 3y squared quantity squared. But don't forget the very last step with implicit, those dy dx's can't be there. So in your final answer, make sure you substitute all of those dy dx's. That thing right there that we found in the beginning. And please don't use arrows, actually put it in. I will try to make the second derivative a little bit easier for you to write out. In that. So there was implicit. And then we bounced to chapter 9 and we looked at parametric and polar derivatives. So parametric dy dx was equal to dy dt over dx dt. dy dt in this case is 8t. dx dt is 15t squared minus 2. So that would be my parametric derivative. And then I could ask you things like, for example, find the slope at the point 36, 17. Or to be more specific, I could ask for the tangent slope. So what you have to do is you have to find the value of t that would make x equal to 36 and y equal to 17. So you would say something like, okay, I need 5t cubed minus 2t to equal 36. I need 4t squared plus 1 to equal 17. So if we solve the second one, which is a little bit easier, you get 4t squared equals 16, t squared equals 4, so t equals 2 or negative 2. Figure out which one works in the first equation, and it turns out to be t equals 2. So at the point 36, 17, your tangent slope, if you substitute in 2, would be 16 over 16 minus 2, which is 58. Your normal slope would be the opposite reciprocal, negative 58 over 16. Some of the other things we did were we did horizontal tangents. So horizontal tangent is when your slope equals 0. So that would be at t equals 0. We did vertical tangents. So that was when your slope does not exist. So if I set the denominator equal to 0, 15 t squared minus 2 equals 0, you get t equals plus or minus the square root of 2/15, which would be when it was vertically tangent. Parametric, we also did second derivatives. So d squared y over dx squared. But if you recall, we're trying to take the derivative with respect to x. However, our first derivative is with respect to t. So we did this the following way. We took the derivative with respect to t of dy dx, and then divided that by additional dx dt. So if I take the derivative of this with respect to t, I'm going to have to use quotient rule. So bottom times the derivative of the top minus the top function times the derivative of the bottom, all over bottom squared. And then all of that, in addition, has to be divided by 15t squared minus 2. So result is going to be 15t squared minus 2 times 8 minus 240t squared all over 15t squared minus 2 cubed. So that was parametric second derivative. Last thing we did in terms of types of derivatives was polar derivatives. So for polar derivative, what we had to do was define x and y. X is equal to r cosine theta. So then you substitute in the equation for r cosine theta. And likewise, y was equal to r sine theta. So that becomes 2 sine theta minus 3 theta sine theta. And then this became basically our parametric derivative. So dy dx was equal to dy d theta over dx d theta. So dy d theta using product rule would be 2 sine theta minus 3 theta cosine theta plus times the derivative of the first, which would be 2 cosine theta minus 3. And then same idea on the bottom. So product rule, 2 sine 3 theta minus 3 theta times negative sine theta plus second cosine theta times the derivative of the first, which would be 2 cosine theta minus 3. We didn't do polar second derivative. We only stuck with polar first derivative. And then I could say something like, find the tangent line at theta equals pi. So then you need an x value. So you go back up here to your x equation. You would get x equals 0 minus 3 pi. Cosine of pi is negative 1. Y would equal 0. Substitute it into your dy dx equation, and you're going to end up with, let's see here, so that would be 3 pi in the numerator, and in the denominator, the first term would be 0, the second term would be 5. So your equation would be y minus 0 equals 3 pi over 5 x minus 3 pi. And then you also had stuff like horizontal tangent, then you would set the numerator equal to 0. Vertical tangent, you would set the denominator equal to 0 and solve for those values of theta. Tangents at the pole, this was actually the easier one. What we had to do was find basically where it crossed the origin. So you set r equal to 0, 1 minus 2 cosine theta equal to 0. Solve for theta, so cosine theta equals 1/2. So theta equals pi over 3 and 5 pi over 3. But we actually stopped there because, if you recall, theta equals pi over 3 actually graphs a line in polar form. So 1 minus 2 cosine theta is a cardioid. It looks something like this. So theta equals pi over 3 is the line that goes to the origin at an angle of pi over 3, and that's tangent to the pole. And then theta equals 5 pi over 3 is the other one. So you could actually stop there for your equations of line as a result. Okay, time for the application type problem. So position, velocity, acceleration. For this particular problem, I want to find the total distance traveled between t equals 0 and t equals 10. So the first thing you have to do is to see if it actually changes direction. And you do that by seeing when the velocity, 6t squared, minus 54t plus 48 is equal to 0. When the velocity is positive, it's moving to the right. When velocity is negative, it's moving to the left. So if we factor out a t squared minus 9t plus 8 equals 0, you get t minus 1, t minus 8. So it changes direction at t equals 1 and t equals 8. So you have to find the position at 0, which is 1, the position at 1, which is 24, the position at 8, which is negative 319, and the position at 10, which is negative 219. Then you have to calculate the total distance traveled between each of these pieces. So 23, and then 343, and then 100 units. Add that all up, and you get 466 units being the total distance traveled. Acceleration was the second derivative, but remember both of those are instantaneous. If I ask for the average velocity between t equals 1 and t equals 5, you're not going to use your first derivative. You're just going to find the position at 1 minus the position at 5 all over 5 minus 1. Because average velocity is just change in position over change in time. Now if I could jump just for a second, we talked about in chapter 4 another way to calculate total distance. Total distance was the integral from 0 to 10 in this example of the absolute value of velocity. So you're more than welcome to use that if you have a calculator to calculate total distance as well. Okay, so on to our last topic, related rates. So in this case, I have a cone, and water is entering the cone at 9 cubic feet per minute. Our cone has a radius of 5 and a height of 8. And our water is somewhere in here with a radius of r and h. So formula for the volume of the cone is 1/3 pi r squared h. And the first thing we did was we used similar triangles to find a relationship between r and h so that we can reduce the variables working here. So r is to h as 5 is to 8. So r equals 5/8 h. So we're going to put that in here. So 1/3 pi 5/8 h squared times h. And if I simplify this, I get volume equals 25 pi over 192 h cubed, I believe. Okay. So now we take the derivative of both sides with respect to time. So make sure you actually write rates on both sides. Don't just write dv because that represents change in volume. It doesn't represent a rate. So this side here will be 3h squared dh dt. And then you go back to your original to see what information is given. Water runs into the tank at a rate of 9 cubic feet per minute. So if you look at the units, that has to be a volume number. 9 equals 25 pi over 192. Water level is changing when it is 6 feet deep, so that's our h. And now you can solve for dh dt. So dh dt equals 0.204 feet per minute. Okay. Don't forget, if it's a cylinder, you don't have to do the similar triangles because the radius is always the same in a cylinder. And the last one is a shadow problem. So I have a woman who is 5 feet tall. She's walking towards a lamppost that's 20 feet tall. And she's walking towards it at a rate of 6.5 feet per second. The question is, how fast is the length of the shadow behind the woman changing when she's 3 feet away from the base of the light? So with shadow problems, it was always helpful to actually draw the figure so that you could see the similar triangles. So I've got a little triangle here, so 5 over y. I've got a larger triangle over here, so that would be like 20 over x plus y. Multiply to simplify, so you get 5x plus 5y equals 20y. 5x equals 15y, x equals 3y. Take the derivative of both sides with respect to time. dx dt equals 3 dy dt. The woman is walking at a rate of 6.5 feet per second towards the light. So that has to be a dx dt. And because x is shrinking, you actually want to represent dx dt as negative. So negative 6.5 equals 3 dy dt. So dy dt is equal to negative 6.5 over 3 feet per second. I only picked a couple of ones to work on, so definitely come see me if you have any questions on other types of related rates.